Lesson involves one more category of word problems, and those are going to be word problems involving motion or things in motion. Now we need to understand that these problems, the majority of them, can be broken down into three types. Now the first type of problem is going to involve two objects, and these problems most always involve two objects in motion. The first type is two objects which are heading out at different rates or different speeds and heading out in opposite directions. Since they are heading away from each other in opposite directions and traveling at different speeds, then they're each going to travel two different distances. The problem will usually discuss or ask for the total distance between the two objects after a certain amount of time has lapsed. Since they are starting at the same point but heading off in opposite directions, the distance between them is simply going to be the sum of the two distances that they have traveled. A similar problem is one where two objects start at two separate locations but then head towards one another. Now again, one is typically moving faster than the other, so that will be represented by two different distances, and the distance that they cover all together once they meet up with one another is again going to be the sum of those two distances. Now the one type that is slightly different from these two is the situation in which two objects, and again we could be talking about airplanes or trains or anything else in motion, bicycles for that example. But anyway, two objects starting at the same location, heading in the same direction. But again, one's moving faster than the other. So what happens is a distance forms between them. One pulls ahead of the other. As before, they've traveled two different distances, but this time around, we're going to subtract those two distances. Again, that would give us the distance between the two after a certain amount of time has passed. Now another helpful tool with this type of problem is a box that you can build to organize your information. The box will have two rows. One row for each object, each train or plane or car or bicyclist or whatever. Then you're going to have three columns. The first column is where you can put distances. In the second one you can put rates. In the last one you can put times. And the columns will be related by the distance, rate, time formula, which says that distance equals rate times time. So I could literally take a value in the rate column, a value in the time column, multiply it, and place it in the distance column. Because with this box, the general rule is you want to fill in two columns with the information from the problem. You want to multiply, sometimes divide, to fill in the last column. And within the problem there should be one piece of information at least that you leave behind to use in your final equation. Alright, so with these three types of scenarios in mind, and with this box in mind, let's start looking at our first problem. In our first problem, you have two people walking, a Will and a Shannon. Now, Will is walking at a pace of 3 miles per hour. Shannon is walking at a pace of 4 miles per hour. So with this information, we can go ahead and start building our box. We will have a row for Will and a row for Shannon, and we'll have 1, 2, 3 columns, a distance, a rate, and a time. And clearly what we've been given is rate. So we'll fill those in the appropriate places. We read on and we see that the question is asking for how long will it take before they are out of range if the walkie-talkies that they're communicating with has a range of 16.8 miles. Alright, now since they've specifically asked for time, that's something we can put in the box. We don't put it in as a known value because they didn't give us a numerical value, but it was the question that was being asked, so it will go in a variable form. And yes, filling in a column with a variable does count as getting the box, partially filled in. Again, the relationship is distance equals rate times time. So I will multiply these two together, and I've got something to fill in my distance box. Now, it was said that these two people are walking in opposite directions. So if we look back at our three situations, we see that this matches the first of the three. So we would simply take these two distances, 3t plus 4t, and set it equal to the distance that's going to be between them when the walkie-talkies quit working. So now we can add our like terms, and when we divide, we'll go to the calculator and take a 16.8 and divide it by 7, and from that we get a 2.4. So our time is going to be 2.4 hours. Now let's look at our next example. We'll clear the board and look at an example where one of the other types of scenarios is taking place. Let's say that there is an earthquake. Now understand that when you have an earthquake, there's a center, and the effects of the earthquake go out in a circular pattern. Now when there's an earthquake, there are two types of waves. There are going to be P waves and S waves. Your P waves travel faster, but the S waves do more damage. And what's going to happen, since the P waves are faster, is that over time a space will develop between them. Alright, so let's see if we can come up with some numbers to fill in to the box. Again, we'll have a row for P waves, a row for S waves, a column for distance, a column for rate, and a column for time, and distance will equal rate times time. Let's see what we know about these two types of waves. P waves have a velocity of 3.6 miles per second, while S waves have a velocity of 1.8 miles per second. And the question is asking how long. As soon as I say how long, you know it's t that you're looking for. And the question says how long before they are 80 miles apart. Now don't be tempted to come up here and put an 80 in for distance. This is not saying that the P waves or the S waves, one or the other, have traveled 80 miles necessarily, just that they are 80 miles apart. Now remember, this is a case where you have two objects heading off in the same direction, so we're going to end up subtracting those distances. So let's fill in something for distance. We're going to have a 3.6t and a 1.8t, and again, like we just said, we need to subtract those two distances, and that accounts for the 80 miles between. Alright, so let's do our subtraction. Let's take 3.6 and subtract a 1.8, and from that we get a 1.8. So we have a 1.8t equaling 80. When I divide off the 1.8, let's see what that's going to give us. 80 divided by that previous answer of 1.8 is a 44.4. So basically we got 44.4, and that's going to be in seconds because our rate was originally given in seconds. So only 44.4 seconds before those two types of waves are 80 miles away from one another. Now we've looked at an example of the distances being added because heading in opposite directions. We've looked at an example of heading off in the same direction. Now we need to see one where we're coming in from two different sides to the same point. Now let's clear off the calculator and get ready for our next example. Now our next example is going to be a road crew. You have a stretch of road that's being paved. 2 crews are working on it, starting at opposite ends of the road and planning on meeting in the middle. So let's get some facts here. We have 2 paving crews, and again we're going to need the box. We're going to have a crew that's moving a little bit faster and a crew that's moving a little bit slower. We'll have a distance for each, a rate for each, and a time for each. And let's see what they tell us. They say 2 crews are laying blacktop on the road. They start at the same time at opposite ends of the road, and it's a 12-mile road. So again, with that 12 miles, that's not the distance for one or the other because neither one's doing it by themselves. That's the distance they have to pave together. One crew can lay blacktop at an average rate of 0.75 miles a day faster than the other. So what they're giving us is not the actual rate for either one, but a comparison between the 2 rates. So I can call the slow crew R and the faster crew R plus 0.75 because they've made that comparison. They tell us that they will meet up at the middle of the project 3.2 days later. So we have a time for each, and again we need to fill in the distance box. This is going to be a 3.2 R because I can multiply. This is going to be a 3.2 R plus, and I need to distribute. So again to the calculator, 3.2 times the 0.75 is going to give us a 2.4. And again, that 2.4 is actually representing the extra work that the faster crew is going to do. So, again, as we've said, these distances are going to be added because they've started in opposite locations and are coming towards one another. So I'll simply take the 3.2R plus the 2.4 plus the other one, which is 3.2R. Combine like terms. 3.2 and 3.2 is a 6.4R plus a 2.4 equaling 12. Now I need to subtract. Take the 12 minus that previous answer, and we get a 9.6. Dividing off the 6.4, it's going to give us our rate. And it comes out a 1.5. So it appears that one crew, that would be the slower crew, that's what we chose for R, is doing 1.5 miles a day. So that's the slow crew. If you don't know how fast the faster crew is moving, then we need to go back and add a 0.75 to that, and that's an answer of 2.25. So that's the rate for each crew. So there is an example for you of each one of the 3 types of motion problems you're going to face, and also showing how the box can be used to organize your information and to come up with the equation that will solve the problem for you.